Okay, we're ready? Okay, welcome back, and Merry Christmas in case you are celebrating. This is the first time I'm giving a lecture on December 25th. It's very unusual for me. There is a first time for everything. Okay, so last week we talked about some ways of remedying the high cost of inner products in the conjugate gradient method. Right? We talked about how the conjugate gradient method could overlap the dot products in one phase with the sparse matrix vector product in each iteration. And today I want to get to talking about another remedy, which is called the S-step conjugate gradient method. And in general, there are S-step Krylov subspace methods, like S-step GMRes. And in these methods, the idea to remedy the high cost of the dot products is to take some number of steps, S steps, of the method, and then during these S steps, there are no inner products, so there's no global type of communication, no global synchronization. And after these S steps, that's when the inner products happen. Okay, so that way we can do S steps without any inner products, and then do essentially all of the inner products together. Okay, now to get there, it is good to talk first, I think, about to give you some background that will help you understand the method. And the background I want to give you falls under the category of projection methods. And it's a very good background to have in case you don't have it already, to understand iterative methods, in particular Krylov subspace methods, in a very general framework. I'm just going to go through it very quickly, and you can find more details elsewhere, but I'm going to go through some of the essential details, especially those that will be helpful to understand these S-step methods. So projection methods, let's say a projection method for solving AX equals to B. The system AX equals to B seeks an approximate solution of a particular form we'll call the approximate solution X tilde in today's lecture. It seeks the approximate solution in the affine subspace x0, which is a vector, plus the subspace K. So I'm abusing notation a little bit. So K is a subspace. X0 is some translation of that subspace. And we're going to assume that K has dimension M. Okay, there are two main ways of choosing the solution from the subspace. And the first is called error projection. The second is called residual projection, but I'm going to talk about error projection. I'm going to focus on error projection. I'll talk a little bit about residual projection. Error projection is an example of the error projection method is conjugate gradient. Okay, and it assumes, in particular, that the matrix A, this matrix A, is SPD. So, for example, the CG method is an error projection method. And the idea is that we're going to choose the approximate solution x tilde as the argument that minimizes the A norm of the error. So if x star is the solution, and x is this argument, x tilde will be the x that minimizes the A norm of the error for all x that belongs to the affine subspace. Okay? So among all x that's in the subspace, the solution x tilde is going to be the one that minimizes the A norm of the error. Okay, and conjugate gradient does this. Okay, it does. We didn't prove, in my lecture at least, we didn't prove that it does this, but you can show that this happens. And we're going to now work from this idea, and from this idea you can derive the conjugate gradient method as well. So you could derive it not from optimization principles, which is what we did before, but you can do it from trying to minimize or solving this projection problem. Okay, so how do we find x tilde? Well, in this expression it's a little bit weird because we have x star, which contains the solution, and we don't know the solution, so how do we minimize this? So let's rewrite it. X star minus x. X star minus x is just the error. I'm going to call that E. Okay? So the A norm of that, and for convenience I'm going to write the square of it here. This is E transpose A times E. So that's also gives you the definition of the A norm, right? It's the inner product of the vectors with A in between. A is, again, symmetric and positive definite. Okay? But of course, we don't know the error, but we know the residual. And this is the same as writing R transpose A inverse. So A times E is equal to R. This is called the residual equation. Let me write that down as well. Let me put the E's in brackets. Okay, so as an aside, the following is called the residual. The following is called the error equation. And I want to be clear about it because we're going to use it a lot in upcoming lectures. So if we have if we're solving AX equals to B, then B minus A times X star, where X star is the solution, this is equal to just 0, right? And B minus AX, where X is some approximate solution, this is equal to the residual. Okay? Then we subtract, and what we end up with is A times E, where E is equal to X star minus X. This is equal to R. Okay? And I've just reversed it here. Okay, so this I can write as the A inverse norm squared of R. All right, so instead of trying to minimize this thing which contains a solution, we're going to try to minimize this residual in this A inverse norm. Okay, so minimize the residual. The residual is just B minus AX, this A inverse norm. And again, this is for all x that belongs to this affine subspace. Okay. And instead of having this thing, this complicated thing, we could rewrite x as x0 plus some linear combination of basis vectors that span this subspace K. Okay? So we could write this as minimum of B minus AX, where x is x0 plus, let's say V is a vector, a matrix whose columns are a basis for the m-dimensional subspace K. So V has m columns. And let's say Y is the vector that specifies the linear combination of those columns. Okay, so as a note where we've written, where we can write x tilde is equal to x0 plus Vy. V is a matrix of basis vectors for the subspace K. Okay. So this can be simplified. So B minus AX0, that's just R0. So by the way, so this minimization now is over Y, right, rather than over this complicated thing. So any Y in m-dimensional space. So R0 minus AVY in the A inverse norm. And the A inverse norm is a little bit weird, so I'm just going to bring this inside the norm. I'm going to split it in half. So A square root R0 minus AVY. So now this becomes a 2 norm. And just cleaning this up a little bit, square root of A times R0 minus, sorry, this is not the square root, this is the inverse square root. Square root belongs over here. Okay. Inverse square root of A times a vector. This is just a vector of length n by 1. Right? And square root of A times V, this is a matrix of size n by m. And Y is a vector of size m by 1. And Y is what we're seeking. So to find Y, this is just the least squares problem, right, with this matrix and this right-hand side. So this is a least squares problem. It has a formal solution. Well, I can rewrite the least squares problem using the normal equations, and then you can see what the normal solutions looks like. So I'll take the matrix and I'll transpose it. So inverse square root of A times V transpose times inverse square root of A times V. So that's the normal equations matrix times Y is equal to inverse square root of A times V, and then the vector, which is I think these are not inverse square roots. These are just square roots. Sorry. Square root of A times V, right? And then the vector is A inverse square root times R0. So if we solve this linear equation with symmetric matrix, then we get Y. This is the formal way of doing it, assuming that square root of A times V is full rank, which it is. Okay, so simplifying this, we get V transpose times A times V times Y. So that simplifies very nicely. And on this side, we also simplify very nicely. We get V transpose times R0. Okay, so the least squares problem is easy to solve if we have this basis V. And if we solve the problem and we plug it back into here, plug Y back into here to get X tilde, solution X tilde is equal to X0 plus V transpose AV inverse V transpose R0. Now the conjugate gradient method is this method with a very specific choice of V. Well, actually not a very specific. It is a very specific choice of V. But even more generally, it's equivalent to any method with a very specific choice of this subspace K. For the CG method, K is the Krylov subspace I'm going to call it Km. And the Krylov subspace takes two parameters. One is a matrix and one is a vector. The matrix A, the vector R0, and it's defined as follows. It's the span of these vectors, R0, A times R0, A squared times R0, all the way up to A m minus 1 times R0. Okay, so there are m vectors I've written down here. And actually, to be very precise, if I take these m vectors, the dimension of this space might not be m. It might be less than m. Okay, but I'm going to ignore that fact. For simplicity, I'm going to ignore that fact. So if these are linearly independent, then we have then these vectors span an m-dimensional space, and that space is called a Krylov subspace. For this method to work, you can use any set of independent vectors in the matrix V, and that would give you a different method. So for instance, the Gauss-Seidel method is actually a method that looks like this. It is an error projection method with V chosen in a very specific way. Okay? And remember, in all of these methods, we have this property that as we take more steps, as m increases, right, these Krylov subspaces are nested. As m increases, then we reduce the A norm of the error in this larger space. And that means that the A norm of the error has to decrease in size, which we'll see in a moment in a slightly different way. But for now, I'd like to answer the question, why is this called error projection? Okay? Why is this called error projection? And it's, I think, instructive to see where this term comes from. Let this matrix W be A times V. Okay? And I'm going to write down this method again, but slightly differently. X tilde is equal to x0 plus V transpose A V inverse V transpose. And instead of writing R, I'm going to first insert A times A inverse before I write the R. Okay? And if we substitute the W, you can see that this is equal to W transpose. So V transpose A is equal to W transpose. And here's another V transpose A. So that's W transpose. And A inverse times R0, what is that? That's still on the board. Using the error equation, that's equal to E0. So this is the initial error. Right? We don't know the error because we normally can't apply A inverse to anything. Right? But the expression A inverse R0 is the initial error. So we can write this as x tilde equals x0 plus V times W transpose V inverse W transpose E0. This quantity you may recognize as a projector. I'm going to call that P. Okay, so what is a projector? A projector is any operator where when you apply it to a vector and then you apply it again to the result, it doesn't change the result, which means that P squared is equal to P. So you apply P to a vector twice, it's equal to just applying to it once. Okay, so you can also think of it this way. I'm going to take a point and project it onto a lower dimensional subspace. And if I apply it again, then it's not going to change. Okay? And you can verify that this is a projector if you just multiply it out, or if you just square it. V W transpose V inverse W transpose. So here's one of them. And V W transpose V inverse W transpose. Here's the second one of them. And you can see there's a V transpose V that cancels out one of these inverses. So you get back the same thing. Okay? So here P is a projector. and specifically it's onto the space that is spanned by the columns of V orthogonally to the space spanned by the columns of W. Okay? So this projector has this matrix form, where V's and W's are bases for two spaces. So the error after one step, or you can think of it as m steps, but the error associated with x tilde, we can get that by taking this expression and subtracting the exact solution x star from both sides. So x tilde minus x star, or actually we could do the reverse, x star minus x, right? That is just equal to e tilde. And on the right-hand side, that's equal to E0. And I guess I'll get a minus if I do that. And this is V, W transpose V inverse, W transpose E0. You can rewrite that as I minus V, W transpose V inverse, W transpose, all times E0. Okay? So if this thing is a projector, I minus a projector is also a projector onto the complement space. So you can see that the new error is a projection of the original error. That's why we have this method called error projection. And if we take norms of both sides in the A norm, okay, so this projector is orthogonal in the A inner product. So it has A norm equal to 1. Okay, all projectors have 2 norm equal to 1. But in particular, this is orthogonal in the A inner product, so it also has A norm equal to 1. Okay, so that means we can bound the A norm of the error from above by the A norm of the error at E0, A norm of the initial error. Okay, so this says what I said earlier, which is that the error has to decrease. Right, the error is always going to be, well, the error cannot increase. Okay, any questions about this? Okay, so this is a very, very brief introduction to error projection methods. Again, conjugate gradient is an example of one of these. But before I go on to conjugate gradient, because there are two types of projection methods, error projection and residual projection, I think it is very useful to also briefly talk about residual projection, just so that you can see both of them. Okay? So I'm going to start over here. So in error projection, we chose an approximate solution this way. What is another way of choosing the approximate solution? Instead of minimizing a norm of the error, we can minimize a norm of the residual. Okay, so we're going to choose x tilde as the x that minimizes the residual, b minus ax, in the 2 norm now, where x again belongs to this affine subspace. Okay, so I didn't erase this first thing, so you can compare what residual projection looks like compared to error projection. As before, we can write x is equal to x0 plus some v times y. Okay, and that means instead of minimizing over this affine subspace, we just minimize over our vectors y in m-dimensional space. Substituting like before, b minus a times x, and x is equal to x0 plus v times y. And this again is a least squares problem, which has formal solution. You can write it out on your own. Write out the steps on your own. It has this formal solution. X tilde is equal to x0 plus v times v transpose a v inverse v transpose a transpose r0. In residual projection, we don't need A to be symmetric positive definite because there is no A inner product being used, right? So that's why I'm being specific about A transpose here. And you can compare that x tilde to this x tilde. So it looks very similar, right? And residual projection, an example of residual projection is the GMRes method. So for instance, GMRes, which is the most popular or one of the most popular methods for solving non-symmetric systems of equations by iterative methods. Okay? And we can also ask the question, well, why is this called residual projection? Right? And to answer that, let W is equal to A times V as before. And X tilde is equal to X0 plus, okay, I'm going to write the first line again, but I'm going to write it slightly differently. This time I'm going to insert A inverse times A on the left side. Then we have V transpose A V inverse V transpose A transpose V times R0. Whoops, I didn't need this extra V. Just need an R0. So now we can identify all these W's. There's a W over here. W transpose. Sorry, that's a W. And then W transpose. So that can be written as X tilde is equal to X0 plus A inverse times W W transpose W inverse W transpose R0. And this you may recognize as also a projector. In fact, it's a slightly more restricted form of this projector. So it's a projector onto the column space of W orthogonal to the column space of W. And what is the residual at the next step? Okay. So the residual R tilde is equal to B minus AX tilde. That's the residual at the next step. That's equal to B minus A times X tilde, and I can just substitute in this X tilde, X0 plus A inverse W transpose W inverse W transpose R0. And here you'll see the residual pop out, R0. And you'll see that this A and this A inverse cancel. So we're left with minus W transpose W inverse W transpose R0. And collecting the R0s, I minus W transpose W inverse W transpose, all multiplied by R0. So you can see that there's a lot of similarity to what we wrote before for error projection, where we have this projector applied to the initial residual. So this is residual projection. And like before, we can say that the norm of the residual, taking norms on both sides, is bounded by the norm of the initial residual. In GMRes, this subspace K is the Krylov subspace. In fact, it's the same Krylov subspace, Km A times A comma R0. Remember, R0 is a good search direction because it's the steepest descent direction. All of these methods start off with taking the steepest descent direction, and then they kind of change in the next directions that they search in, right? Well, sorry, I shouldn't say that. They kind of change in what they're trying to optimize in this subspace. Any questions about this? Okay, so now we could talk about the S-step CG method. Okay, the idea, as I said before, is that we're going to try to take S steps of the conjugate gradient method without any dot products and only do global synchronization if we're running in parallel, only do these synchronizations after S steps. Okay, so we're going to do S steps without dot products. We then do computations with dot products all together. So this is a little bit like what we saw before, right? The classical conjugate gradient method has 2 dot products per iteration. And one of the first things we did was to rewrite the algorithm so that the 2 dot products are combined. You could do the 2 dot products at the same time, right? So that there's only one synchronization in the one synchronization per iteration. Okay, so now this idea is, well, how can we do even less synchronization per iteration? And the idea is to take S steps before we actually synchronize. Okay, so we do this, and then we repeat. Do S steps, do some computations, do S steps, and do some computations. And to be clear, let's say that normally we need dot products to compute the step lengths alpha k and the conjugation constants beta k. Right? So remember, when we're computing these alphas and betas, we needed dot products. So the idea in S step, as I've been saying, is that we're going to search in an S-dimensional subspace that minimizes the A norm of the error. That's what the conjugate gradient method does. Right? And you can notice that I think I've erased the expression for error projection, but remember, it looks something like this, right? In fact, it looks something like this, and in particular, inside here, we don't have the A transpose. So this does not involve, to do this, this does not involve any dot products, assuming that we have some way of forming and solving with this matrix, right? So that's like doing S steps. Here I called it, instead of S, I called it M. Right? So here, this method is doing M steps, and then we're stopping, but we're finding a solution that minimizes the A norm of the error in the subspace. So we're going to search in S-dimensional subspace. And to do this, we have one stage of dot products. You'll see in a moment. That minimizes the A norm of the error. Okay, and then what should we do next? We've taken these S steps. Now we're going to take another S steps, right? but we're going to try to make sure that the search directions in this second cycle of S steps do not overlap with the search directions in the first cycle. Because if they overlap, then we're not searching efficiently. Then search in another S-dimensional subspace. And actually, it can't be any S-dimensional subspace. It's going to be a very specific S-dimensional subspace. That is conjugate, aorthogonal or conjugate to the first subspace. So if it's not clear, these vectors v span the search directions, right? And in the conjugate gradient method, we saw that the search directions are kept aorthogonal or conjugate to each other, right? So now instead of making the search directions within the first S steps conjugate to each other, we can't do that because if we wanted to do that, we have to do dot products. But we're not allowed to do dot products. But what we can do is, after we've done S steps, is to make the second cycle's search directions orthogonal to the search directions in the first cycle. Okay, so that's what's meant over here. We're going to search in another S-dimensional subspace that is conjugate to the first subspace. And then we repeat. And we always make, whenever we repeat, we always make the new subspace conjugate to the previous subspace. And not all previous subspaces. We only need to make a conjugate with the last subspace. Just like in the conjugate gradient method. We don't need to conjugate against all of the previous vectors, search directions, just the previous one. Okay? So that's the idea. I think now we're ready to write down what the algorithm looks like. And I'm going to point out that I'm going to write the algorithm in a very simple way, in a way that I hope is understandable conceptually. And in a real implementation, you would not implement it this way because it is not the most efficient way of implementing it. And there turns out that, well, this topic is highly of interest to a lot of people. So a lot of people have written papers about this, which means that there are a lot of variations of this S-step conjugate gradient method and indeed of Krylov subspace methods in general. Okay, but I'm going to write down a version that is primarily conceptual. Okay, that is going to try to write down precisely in math what these ideas are over here. Okay, so of course we're given an initial guess for a solution x0. Okay, and we can define R0 as the initial residual, just like before. All right, so nothing is scary yet. Okay, so now comes the scary part. We're going to do S steps. So we need S search directions. What should those search directions be? I'm going to call the matrix of search directions capital P0. So what should those search directions be? we know that R0 is a good search direction, right? The other search directions are going to be A times R0, A squared times R0, all the way up to AS minus 1 times R0. So this is S vectors. Right? So instead of searching in just this one-dimensional space, we're going to search in an S-dimensional space. And basically this P is a basis, at least at this stage, it will actually always be later on as well. This P is a basis for the space that we want to search in, that we want to find our correction in. That corresponds to this space K. Right? So in fact, we've constructed some basis for the Krylov subspace. And if you've seen something like this before, you know that this is a very ill-conditioned basis. I'm going to ignore that fact for now, and next lecture I'm going to address how that can be fixed, or mostly fixed. Okay? So now let's begin our loop. So I is equal to, let's say 0. And I is going to be an index that indices every S steps. So the initial, not the initial, but the next approximation is equal to the previous approximation plus something. So what is the correction to X that conjugate gradient gives you? In other words, it's the one that has to minimize the A norm of the error in this search space. Right? And we wrote that down before. Instead of V, I'm going to write PI. Right? So this is the error projection. Right? I didn't insert the A inverse A, so there's still a residual over here. And this involves dot products. It involves the dot products put together. Okay, notice that when we generated these S vectors, we didn't do any dot products. Okay, so this is the next solution. Okay, what should we do next? We can update the residual as usual. And I'm going to write down a formula that just updates the residual explicitly rather than recursively. And that's probably going to be necessary because of the ill condition that I just mentioned. We probably want to try to use the real residual here rather than some residual computed recursively. Okay, now we have to get ready for the next step. Right? So at the next step, in the classical conjugate gradient method, we compute a residual, and then we make that residual conjugate to the previous search directions, and that becomes a new search direction. But we need to have M search directions. So we're going to take this residual, and we're going to make S of S residuals. We're going to make S vectors. I'm going to call that capital Ri. So that's going to be a matrix of S vectors. So what should these vectors b. In the classical method, and the classical method is going to be the same as this, assuming that s is equal to 1. Okay, so if we were just trying to match the classical method, then this has to be ri plus 1, right? Because this is the residual that we're going to conjugate later on. So what should the other vectors be? Next one will be a times ri plus 1. Then a squared times ri plus 1, all the way up to a s minus 1 ri minus 1, r plus 1. Right, so this is s vectors. And to compute these s vectors, we need to perform s matrix vector multiplications, all without any dot products. Okay? And in the conjugate gradient method, we need to construct the search directions. So the new PIs, we have the initial set of search directions. The new search directions are going to be the residuals conjugated with all of the previous residuals. Okay, so that's going to be equal to Ri, capital Ri, this thing that we just computed. And to make these, let me do something, correct something in the notation that I have. I'm going to call this capital Ri plus 1 to match that Ri plus 1. And this capital Pi plus 1. Okay, so these are all quantities that we're going to compute now in preparation for the next step. So to take a residual vector and to make it conjugate with a set of vectors, we're going to subtract some combination of these previous vectors. We're going to subtract components of these previous vectors. So I'm going to write that very generally as plus, these are the previous vectors, pi, times some matrix B. Right? So I have my current vector, current residual. I'm going to subtract different combinations of these previous vectors such that, so B is just some vector of, some matrix of coefficients that kind of corresponds to the beta. Actually, they do correspond to the beta that we have in the classical conjugate gradient method. So we're going to do this such that the vectors in Pi plus 1 are conjugate to the vectors in Pi. Right? We want these search directions to be not overlapping with the previous search directions. If we overlap, then we're not going to maintain the property of the conjugate gradient method. Okay, so how do we choose P in order for this to not overlap? It's very simple. We just force this conjugacy condition. So if we take Pi transpose and we multiply it by Pi plus 1 with A in between, that has to equal 0, right, in order for these vectors to be conjugate. So in particular, within Pi and Pi plus 1, the vectors are not conjugate with each other. Right? We can't do that. If we wanted to do that, we would have to do dot products. Okay? And in particular, we can't just search in this subspace, right? Because this subspace overlaps with the subspaces that we've already searched in. So we really want to, so this vector, the first search direction that we want to search in would be one that's conjugate to all the previous search directions. But we have no way of constructing that in this new algorithm, right? Okay, so this is the condition, and this gives us what B is. So Pi transpose A, Pi plus 1 is just substituting Ri plus 1 plus Pi B is equal to 0. And you can solve this to give you B is equal to minus Pi transpose A Pi inverse times Pi transpose A Ri plus 1. Okay? So we can solve for the betas. And then using this beta, we can compute the new search directions. And then end loop. This is where the loop ends. And we repeat. Okay, so conceptually it's very simple. We're searching in an S-dimensional subspace at a time, and we're making sure that these S-dimensional subspaces are A orthogonal to the previous one. And in fact, it'll turn out to be to all of the previous ones. Okay? But you would not implement this way. One is because these quantities kind of imply that you're doing additional matrix vector products over here and over here. But there are easy ways of computing these things. Well, actually, there are cheap ways of computing these things that don't involve doing more matrix vector products, right? Like here is where we've spent up all of our matrix vector products, and we can't do any more of them. Mathematically, this algorithm gives us exactly what the conjugate gradient, the classical conjugate gradient algorithm gives us, but only every S steps. So the algorithm mathematically gives iterates that are the same as every S iterates of the conjugate gradient method. So I don't know if you find that pretty amazing or not. So, but to verify your amazement, that will be your exercise. So the exercise is to implement this algorithm in MATLAB. Just pick a simple matrix and don't print out the iterates because that's too much. What you can do is you can print out the residual norms every S steps, meaning print out the norm of this guy. Okay? And then take the same matrix on right-hand side and try it with the classical conjugate gradient algorithm, either one that you've implemented yourself, but you can also use the one that is built into MATLAB, and ask MATLAB to print out all of its residuals. And hopefully you will see that every S steps of the classical conjugate gradient algorithm, the residual norm will be the same as the residual norm that you compute over here. But in your algorithm, you are able to do all of these matrix vector multiplies without doing any kind of synchronization. Right? The synchronization only happens after you've done all this work, and they're basically done together. Okay. Now, as a caution, because this basis, as I'm going to explain next time, is very ill-conditioned, your results may differ numerically. But to try to reduce that effect, you should choose S to be very small. Like you should choose S to be 2 or 3 or something like that, or at least choose a matrix that is very well conditioned. Okay? So let me write down a little bit what I just said about the exercise. So I think this is exercise 6, right? No, exercise 5. Since there was no exercise on Friday, because you had an assignment instead. Exercise 5. Implement S-step CG in MATLAB. Verify mathematical equivalence with classical CG, and then the caution is to choose a small s. Okay? If there are any questions, I'll take them after class. Otherwise, I'll see you tomorrow. Yes? What is usually the value of S that is chosen? That depends on the problem, because it turns out that the numerical difficulties are challenging enough that a very large S cannot be chosen. So we're talking about on the order of 10 or less. So we're not choosing like large values like 50 or 100. Something that is interesting is that S does not have to be constant. You can actually change S as you go along. And it turns out that a fairly good strategy is to start off with small s, and then you can increase s. And there has been some theory that has been developed that says when the S-step method is going to differ numerically from classical. And it has to do with how accurate the residual is. And this residual tends to be better later on. So then you can take a larger s. So for your exercise, I would suggest s equals 2 or 3. And you could try larger, but then you might not be able to check whether or not your code is correct if you start with something large. Any other questions? Okay, see you next time.